In this video, we're talking hypothesis testing, which is really just a nice way to say we want to set up some arguments. We'll talk about an introduction to these hypothesis testing. How do we set them up? What do these procedures or these things look like? And then we'll end with talking about maybe how do these conclusions, or how do we make conclusions based on evidence that hopefully proves our case. Let's dive in here. Confidence intervals and hypothesis testing often go hand in hand. They're very similar because they both take sample information and then apply it to a bigger group, a population. The example here is going to introduce confidence intervals, and then we'll see how that might relate to hypothesis tests. Given some sample information, this is a sample mean, let's say is $12 an hour. You could also talk about sample proportion, but we'll stick with the mean conversation for now. Predicts a range of values for a population mean mu. Again, sample the mean. We say 95% sure that the population mean mu is inside of this interval. And if you'll remember, when we were building these things, we always talked about a left endpoint and a right endpoint, where we needed this ingredient, this margin of error, the swing that told us how wide that interval was going to be. So let's just say we build this interval based on that sample mean, and it looks like our margin of error was $2 because we got a left endpoint of $10 and a right endpoint of $14. That's the smallest I can imagine being and the largest. Intervals built in this way have a 95% chance to contain the population mean mu. And it's somewhere in there. I don't know. It could be $10. It could be 11. It could even be 12. But somewhere in there, we're not quite sure. Sample information into population information. That's a lot of this hypothesis testing. Although for hypothesis testing, we first need to set up an argument. The chart that I have here listed, this shows some information, a lot of different hypothesis tests. And there's some components that I want to highlight for you here, and then we'll get into the granular. This is some socio-demographic characteristics of a study. And they looked at, for instance, this is annual family income proportion or percent that earn less than $12,000. And it's just comparing single parent households versus two parent households. And it looks at the proportions. Now, some of us might look at these proportions and go, wow, there's a huge difference between them. But again, notice that these are technically sample proportions, p-ads. And so somehow when we compare these two, it's very difficult because these are samples. Well, how are we going to make some inference about a larger population group? There's a way to do that. It's two sample hypothesis testing. We get this p-value. And as you go down, there's some other categories. In fact, there's many hypothesis tests that were performed. But some of these don't have a p-value. They have this NS down below. That's actually very important. They include that. NS stands for not significant, meaning that, look, even though there was a difference, this is race non-white for single versus two. And although there was a perceived difference, that difference was not significant, or they couldn't state any kind of significance between them. Now you might be asking, how in the world do we define or make a threshold? It's actually right over here. This is a threshold for what we call not significant. We'll talk more about that. I'll put a little character for later. Alpha, it's the Greek character A, for reference later. So this is what the results of hypothesis tests look like. Specifically for two sample, we'll focus on one, where we have these changes. We look at samples and somehow infer something about a population. Let's dive into aspects of a hypothesis test. So first we need to set this thing up. Hypothesis is really just a nice way to say claim. Particularly, we talk about claims for a population parameter. That could be the population mean, like mu, or the population proportion, like p. Sometimes you'll see it written as prop to help differentiate it from p, a probability we'll talk about later. When performing these tests, we first have to identify what the claims are, and there should always be two, at least the way we'll set these tests up. The first, the null hypothesis, and the second, the alternative hypothesis. For the null hypothesis, this is oftentimes abbreviated HO, and these should always be, again, claims that are being made. A classic claim might be something like, hey, look, the mean is equal to, I'll talk about maybe 11 feet. One thing you'll notice about these null hypothesis is it's always going to be an equal to situation, very one-dimensional. They're always going to claim, hey, look, it's 11 feet, don't worry about it. And this is always assumed to be true. In fact, oftentimes they call the null hypothesis the status quo. It is what it is, and it is what it always has been. Assumed true. But we're stepping up, we're setting this argument because we have an alternative hypothesis. This is what we want to show, or you can think about it saying like we want to prove something. HA. And again, these should be claims or statements. And I disagree with your 11 feet claim. And I think maybe it's less than, maybe it's greater than. We'll put less than 11 feet. And that's the two arguments. And so we need to set up the argument so that we can know what side of this we're trying to come on. The null hypothesis is what it's been, what it always has been. And the alternative hypothesis is what we're trying to show, we're trying to prove. And so we need to clearly state our arguments. This is the procedure of what these steps look like. From a very zoomed out perspective, we'll talk about the procedures. The first thing, just like we talked about, we have these two hypotheses. Well, you need to state them. What are the two arguments? The null and the alternative. Then we determine what kind of test, or how are we going to test between these two. We generate a test statistic. We'll talk about that. And a level of significance that actually refers to that alpha character, but we'll get to it. Once I figure out the arguments and I figure out what tests I need to perform, well, I need to gather some evidence, some data to hopefully support my claim, what we're trying to prove. And then once that evidence is collected, well, then I can make either a conclusion, either positive, try to prove what we want to prove, or, backing off, I can't make these assertions. On a more zoomed in level, an outline of our hypothesis testing should go something like this. Given population information about the population mean or about population proportion, we need to first set up this argument that, look, this is kind of given to us. They're saying, look, don't worry about it. The height of, let's say, some particular tree is 11 feet. Okay. But what we think our question to ask is, has it changed in some way? And there's really only three types of changes that we can be interested. Either it's not 11 feet anymore, it's greater than 11 feet, or as my little example over here is less than 11 feet. This is our claim we want to show or to prove. Again, you can think about maybe these are boards being produced on an assembly line, and they're like, look, these boards, they're always 11 feet, we're golden, don't worry about it. And I'm on that assembly, I'm looking at these things going like, I'm kind of suspicious. I don't think they're quite producing at 11 feet. I think it's actually less than that. Well, in order to prove my case, I need to gather some evidence. If I'm talking about a population mean, the best evidence would be, we called it a point estimate back in the day, would be a best guess, a sample mean. And so say maybe after gathering, I pulled, let's say 100 different boards, and I got a sample mean of 9 feet. Well, one good question asked then is, does this provide good evidence for my claim? And if I'm saying that it's less than 11 feet, yes, this does provide some evidence. But just like when we were talking about confidence intervals, these two should be close, the population mean and sample mean. But is 9 feet close enough? Is that significant or not? I mean, 9 feet and 11 feet, that could be close enough. Who knows? In order to do that, we need to calculate a p-value. We'll talk more about the p-value later, but this is like our margin of error. This tells us, look, how significant or how wide our interval needs to be. For this pretend example, we have a p-value of, that looks like 5.4%, a little bit greater than 5%. That'll be important later. So I have my evidence, I have my p-value, that's from the test that we'll perform, and then it's time to finally decide and interpret our results. Do I get to make my claim? Do I get to either show off and say, hey, look, my alternative hypothesis is correct, or maybe I have to acquiesce? We'll get into it. The most fundamental part for hypothesis testing is actually stating those hypotheses. And so that's our first example. Read the scenario and determine what the null hypothesis and the alternative hypothesis are. Here's our first example. At Northeast Community College, syllabi for online classes state that students should expect to spend 10 hours per week completing coursework for each 3-credit class. A survey of 231 course-found students, on average, spend 12 hours studying with standard deviation of 3.2 hours. The director of e-learning for the community college is concerned that students are being required to spend an average of more than that 10 hours per week completing coursework. What are the arguments at play? The way I'd encourage you to think about this is the null hypothesis over here, again, it's the status quo. It's what is, what has always been. And really for these arguments, we're really only choosing between a mean or a proportion. For this, up top, if we read syllabus, online classes, expected to spend, expected, there's an average, a mean, we're talking about a mean here. Additionally, for these null hypotheses, these will always be equal to. We're never going to mess with that. And if we read the scenario, they're talking about an average of 10 hours per week studying. And then this average over here, this 12 hours, this is anecdotal. This is just from talking to those 231 students, found that average with a sample, technically standard deviation of 3.2 hours. And so the mean, the status quo, is the average for the population mean, which is 10 hours per week studying. It is what it is. Don't worry about it. That's what all students are doing. We're a little suspicious. We think they might be mistaken, but that's certainly the claim out there. And now we have the alternative hypothesis. Again, this is what you want to show or want to prove. Notice I'm arguing for a mean here. Well, then I'm also going to have a population mean here as well. And for the kind of change that we're interested in, well, again, there's three different options for you. There's not equal to, there's greater than, or there's less than. And those are really the only three options. Well, right up here, it says this director of e-learning thinks that students are being required to spend an average more than 10 hours. That is exactly what we want to show. I want to show that the mean is actually greater than 10 hours. One thing that I want to highlight here for you, little hint, is that notice there is no sample information in these arguments, all right? Because when we're setting up the arguments, I'm trying to state what our side is, and then we're trying to state what the null hypothesis is. We're not bringing anecdotal evidence into our claims. These are the argument, hey, where do I stand? I think it's more than 10 hours. You think it's equal to 10 hours. Okay, well then now I can gather my evidence. And that's what this 12 hours and standard deviation 3.2 is. It's our evidence to hopefully bolster our claim, which looks like 12 greater than 10. That might be some good evidence. We'll have to get into it later. Next example. A car manufacturer advertised that its new subcompact model gets, on average, at least 47 miles per gallon. That's what the advert says. We are suspicious of their claim and suspect some false advertising. If we would like to test this claim and prove the manufacturer wrong, then our hypotheses would be blank. Some key words for you. Again, the null hypothesis, the status quo, it's always a mean or proportion. In this case, we're talking about an average, is always right equal to 47. And technically, this is miles per gallon. That's what their claim is. But we'd like to prove them wrong. Notice the claim here said at least 47 miles per gallon. At least meaning, look, 47 is good for them. They also think it might be 48. It might be even greater than that. In fact, their basic claim, the status quo, is that they're claiming that it's actually greater than, well, or equal to 47 miles per gallon. But when we see that advert, maybe we have friends that drive this car around, and we're like, I don't think you're right at all. I'd like to prove that manufacturer wrong. I want to test against. Again, we suspect some false information. I'd like to prove them wrong. Well, that's exactly what the alternative hypothesis is. This is what we want to show. The beginning is friendly. I know I have my mean, and I also know this has to do with the 47. The only thing that I really need to figure out is if I should do not equal to, if I should do greater than, or if I should do less than. Again, those are the only three types. Those are the only three types of changes that we're interested in investigating. And so if they're claiming that it's at least 47, well, you can think of the opposite of that would be less than 47. And that's what we're ultimately wanting to show or trying to claim here, that it's less than. So these are our two arguments, that the mean is equal to 47 miles per gallon. That's what the null hypothesis is, although it's technically a subtle greater than or equal to, because in order to show our opposite of that false advertising, I'd show that the mean is less than 47. And if I'm true, well, hey, fantastic. I get to say that was false advertising and let the lawsuits begin. That's how these hypothesis tests are set up. Next example. A leading news authority claims that the governor's job approval rating has dropped over the past 3 months. Previous polls put the governor's approval rating at 56%. The governor's chief of staff is concerned about this news report since it's an election year, and he wants to run a test against the news authority, proving the opposite. So again, the opposite of that dropped notion. Well, the status quo, the null hypothesis, again, set this up. It's either going to be the mean or the population proportion P, and it's always going to be equal to. If you have no idea, at least you could start with that. You're either talking about a proportion. In this case, we're talking about an approval rating. You can either write capital P if you'd like, or we can be even more clear and write prop for population proportion. And look, don't worry about it. The population proportion is, it looks like 56%. All right, 0.56. The null hypothesis, nothing's going to change. It is exactly as it's always been. Although really, in the background, we should be thinking of this because the status quo is, or at least what's assumed true, is that it's dropped, that the proportion is less than or equal to this 56%. Because then we want to prove the opposite of that. That's going to help us with our claim, with our alternative hypothesis. Again, this is what we want to show. The framework looks similar. We'll write prop and 0.56. Again, that's always the same And then I'm looking for these 3 different types of changes: not equal to, less than, or greater than. These are the only 3 types of changes I can test for. Well, if they're saying that it's dropped, then I'm trying to prove against that. I want to do the opposite of less than, which will be greater than. And there's the change that we want to show, or at least that's how the argument is going to be set up. Next one. Assume a sample of 800 computer chips reveals that 80% of the chips fail in the first 1,000 hours of their use. Oof, it's a lot of failure. The company's competition's literature claims that over 70% fail in the first 1,000 hours of their use. Is there enough evidence at a 0.02 level to support the competitor's claim? There's a lot going on here, but I think we can break it down. Notice this is a sample of 800 chips, and this 80%, that's a sample proportion p hat. Over here, this 76%, this is referring to a population proportion. It's like the status quo. The competition's literature claims that it's over 76%. Telling you from that sample, it's not looking too good for us. So when we set up the argument, we should always start off with mean and proportion. In this case, we're talking about a proportion, and it's equal to population information, 0.76 or 76%. For the alternative hypothesis, the claim, we should write prop in 0.76, and then we need to think about what our change might be. Again, not equal to, greater than, or less than. This is the claim that's being made. And notice the claim is that it's over 76%, and we're trying to support that claim, over 76%. So this one's simply greater than 0.76. And so when you're setting the arguments, it's very important that we set them up the correct way, because how embarrassing if we set our argument up incorrectly, and then we come and gather sample information that maybe doesn't prove what we're trying to prove. And so it's important we set up our arguments correctly, so then when we build out our case or our evidence, that we support the proper argument, or at least the claim that we're trying to prove. So important first step, set up the argument. How to make a decision though? There's really only 2 decisions to make, and you might think it's either we're right or they're right, but again, they're already assumed to be true. So we're not trying to prove the null hypothesis case. In fact, really the only claim that we can make is right over here, to reject the null hypothesis. I'd encourage you to try to associate that with a positive emotion, because it's a very good thing. Again, the status quo, the null hypothesis, is assumed true. But hopefully, at the end of some work here, we'll get to say, look, bump the old and in with the new. I get to reject the null hypothesis, and I get to accept the alternative hypothesis, which again, I encourage you to think about what we want to show, what we want to prove. So again, it's fireworks go off, we get to set out and claim what we set out to claim. Our argument is correct. Another way to think about this is the evidence. That evidence, I can bring you back to that little anecdotal, the logs being 11 feet of 9 feet. It's going to support our claim, our alternative hypothesis, which if you'll remember back in the day, we said the mean is less than 11 feet, which again is a very good thing. If we get to make this assertion, it's like, look, the evidence we gathered, or our claim that we stood out there and said, we can assert it. So again, fireworks, happy all the way around. The other decision is a failure. It's a failure to reject the null hypothesis. This is the bad case. This is when we set out to gather our evidence and say, maybe I got a sample mean of 12 feet or something like this. It's like, there is absolutely no good evidence to make my assertion. Again, I don't need to, and I should say this is not proving that HO is true and that we're incorrect. Because again, the null hypothesis is assumed true. And so, especially the way the math works with our probability and we do normal distribution stuff, our objective is not to prove the null hypothesis is true. It's assumed true. And so if we simply gather poor evidence, our evidence shows us nothing at all. It doesn't get to make an assertion that we need to. Now we might gather some sample information, maybe adjust. Maybe if we gathered some sample information, found that the average was 14 feet, well then, hey, maybe our claim should be adjusted. Instead, we need to look at greater than 11 feet. In which case we'd have to show that, hey, look, we failed the first time, but we can rework our arguments and we'll get an appropriate p-value. Let's see if we can go through a decision and see what this looks like in practice. Based on historical data, 2018, The Board of Education for one large school district believes that the percentage of high school sophomores considering dropping out of school is at least 10%. Oof, not great. A high school counselor claims that this percentage is too high. They're thinking, look, you guys are making this claim of 10%. I don't think it's quite that high. They conduct a study and find the sample proportion, p-hat, to be 8%. The result is to, fail to reject the null hypothesis. Again, I encourage you to think about that with a negative emotion. Bummer. So again, the school is claiming it's at least 10%. A lot of these kids are dropping out. We're not sure it's at least 10%. High school counselor says, I think you're too high. And he finds a sample portion of 8%, which again looks like some good evidence. But unfortunately, the result was to fail. We didn't get to debunk their claim. Speaking of which, what are the claims? State the hypotheses and we'll fill in some blanks along the way. So for our null hypothesis, the status quo, these are talking about proportions. And so I'll write P for population proportion, or we can be more exact and write prop. Again, these hypotheses are always going to be equal to the null hypothesis. And what's the status quo? This 8% is sample. That's anecdotal. We're not going to include that. It's this at least 10%. At least. But our claim, at least as far as the high school counselor is concerned, is that I think that is actually too high. And we'd like to show that it is indeed too high, that 10%. And so our claim, again, prop and 10%, and what's in between, I think it's too high. So I think it's actually less than 10%. Because again, always this is what we're trying to show. Sometimes we can give you a little hint too, not always, is when we look at the population, the sample, this number is smaller. And so sometimes that can be a little hint as to what argument we're trying to show. It's less than 10. Here's where we get into the brass tacks. If we failed to reject the null hypothesis, what does that mean for our evidence? Again, the evidence was our sample proportion, p-hat, was equal to 8%. Unfortunately, since we failed to reject, then this evidence does not support the claim. And again, the claim is always the alternative hypothesis, that the proportion is less than 10%. Again, we might look at 8% and go, oh yes, it is less than. But in reality, that's not significant enough to say that it actually has changed, that it's not at least 10%. Bummer. Again, everybody walks around sad. The high school counselor's like, man, I had this big claim, I had this big idea. I thought maybe we were making a difference or something. And unfortunately, we failed to reject. But there's still hope, because these claims or these debunks are based on a probability. So what happens if we make a mistake? And I'm sure the high school counselor here is hoping that this was a mistake. What kind of mistakes can we make? There are two kinds of mistakes that are possible, really based on those two decisions. The rejecting, again, very happy about that, versus the failing to reject, very sad about that. And so there's two types of errors based on the rejecting or not rejecting. They go like this. Look, if we reject the null hypothesis and HO is false, well, then we did the correct thing. Again, everybody walks away happy after the fact. We know that we made the right decision. But if we rejected the null hypothesis and it was true the whole time, oof, we made a big error. We call it a type 1 error. That's a big mistake to make. If you reject, and in reality, you should not have rejected because it was true, you made a mistake. We call it a type 1 error. On the flip side of that, in fact, let me write it in green, because sometimes you fail to reject. So if we failed to reject the null hypothesis and it was true, well, then we made the correct decision. If we failed to reject and it was true, well, then we did the right thing. However, if you failed to reject, but you really should have, that's going to be called a type 2 error. So we have these two different types of errors based on rejecting, type 1 error, versus failed to reject, type 2 error. The one that we're really interested, or at least the one we really want to avoid, is the happy day where we reject, but then it turns out, oof, we shouldn't have. In fact, that's the one we want to avoid the most. We want to avoid a type 1 error. So much so that we'll define a threshold for what we mean by how comfortable we are by making that mistake. In fact, we'll talk about a probability of committing a heinous act of a type 1 error. We call the probability of making a type 1 error a level of significance. In fact, it's often denoted by this alpha character. If you remember, alpha was actually related to beta. And so we have these two. Alpha, again, is our level of significance versus beta was our level of confidence. We have significance, we have confidence, and there's a nice relationship between the two. And so alpha has this relationship of 1 minus beta. We had some normal levels of confidence, so we're going to have some normal levels of significance as well. This is 10%, 5%, and 1%. I'll tell y'all, as a rule of thumb, 5% is what we usually go by. In fact, if you remember the table that we showed earlier, it was talking about probability of greater than 0.05, or that 5%. That was our level of significance, or alpha. We'll get to it in a second. This alpha character, you can think about like a threshold. It's basically, look, how comfortable am I making a mistake, or how rigorous do I want to be? For instance, if we set that at 5%, it means if we're less than 5% likely, then that's pretty rare. We consider that rare. But maybe you want to be loose with it, and you're like, hey, look, I think 20% is a good threshold, meaning that if the probability is less than 20%, anywhere in there, that's unlikely, probably not going to happen, which might not be a good thing. We want to have a very strict level of significance. In fact, if we have a level of significance of like 1%, well, that's very strict. There's not much that can happen outside of that 1%. But 5%, like I said, is the rule of thumb. In fact, you'll refer to our table for beta level of confidence and alpha level of significance. We actually get these very important critical values based on different levels of confidence and different levels of significance. These are often referred to as rejection regions. We'll talk about it in a minute. And again, the most common one is 5% level of significance. And so that's why I circled it for you here. We talked earlier about those samples that we gather. Maybe for the length, we said sample mean of 9 feet. Well, how do I know that that's maybe statistically significant or not? It really depends on, we call it a test statistic. And there are a couple different types of test statistics. It really depends on what kind of test you're trying to run. I have a table here to reference. Let me zoom in on it. And that is based on whether or not you're trying to do hypothesis tests for a mean, a sample mean, X bar. You're either going to need a Z test statistic or a T test statistic. And then there's different ways to figure out p-values. We'll talk about that later. And then if we're talking about proportions, there's also a different test statistic or Z value for that as well. And it's this Z value that ultimately will give us a probability. If you don't want to go that extra step in figuring out a p-value, again, this is kind of the old way to do it, is to generate what we call rejection regions. If you'll remember from that table, we have a nice normal distribution. And inside of those Z values, those were critical values for what we consider to be abnormal, or we considered rare. The classic critical value is for that 5% was 1.96. These critical values go positive and negative on opposite sides. And so you can think about that on a normal distribution, that I can actually graph what these are. And so I'll graph one on the positive side and one on the negative side. And anything inside of here we'll consider to be normal. Hey, no big deal. These are normal values, nothing to be afraid of. But if I calculate, let's say, a test statistic, a Z value, using this little formula, and I know 9, let's say, is way outside of the norm. In fact, I think it's, all the way over here, way less than my average that I was claiming of 11 feet. Well, then I think that that provides some strong evidence it's outside of my rejection region. There's actually a little bit more to it, depending on if you're talking about greater than or less than or not equal to. Technically, this is a two-tailed hypothesis test, but I'll leave those granular details for a later date. Because we don't really like rejection regions because the analysis is a little bit more granular. Instead, we use p-values, much like the table that I showed earlier with those various different p-values. Speaking of which, these p-values are a probability. And this probability, often sometimes referred to as an observed level of significance. We're going to make a comparison. We have two levels of significance. One's observed and one is stated. The p-value is a certain probability. And I think this example helps highlight best what the p-value is. So let's take our example from before. We have our null hypothesis. Again, look, it's true. It's always been true that the mean is 11 feet. We suspect there's been some kind of a change. I think it's actually less than 11. So I gather some evidence. I gather the sample mean is 9 feet. Oftentimes this is given to you in the scenario. After you calculate the sample mean, we can look at a probability, right? How likely is it that the population mean is 11 feet, again, as assumed true, and meaning at the same time that the sample that we gathered is also true. Both these things have to be true at the same time. We can talk about a p-value. How likely is that to occur? Sometimes denoted p, or probability, that both of those are true at the same time, that the population mean is equal to 11 and that the sample mean is equal to 9. Well, when I look at these, they're pretty far apart, meaning that I think it's unlikely that if the population mean is 11 and the sample, I think this is unlikely to be the case. In fact, we can quantify exactly what we mean by unlikely, and that's what the p-value is. In fact, we might throw up a p-value of 0.056, roughly 5% chance. Now look, that might be unlikely to you, it might not. It really depends on that level of significance, alpha, what you set it to be. If you set your level of significance to be 10%, well then hey, 5.6% is unlikely. It's below your level of significance. But if you were more rigorous and you're like, you know what, 10% is not enough, and you set it to, let's say, 5%, ooh, just barely above our threshold. And so, you know what, it might sound unlikely to some, but that's actually not considered unlikely to me because my threshold is 5%. And so the big takeaway here, move out of the way a little bit, is the smaller the p-value is, the more likely we are to reject. We want the smallest p-value, the smallest probability as possible, because the smaller it is, the stronger our evidence is to reject, or in other ways, you could say against the null hypothesis. So we want smaller p-values because, again, it's a likelihood that two things are true at the same time, and we want that to be unlikely. And so much like I was alluding to earlier when we talked about p-value, comparing it with our level of significance, the two decisions, the rejecting, again, I encourage you to associate that with a positive emotion, and failing to reject, not happy about that. Those decisions are solely based on this one comparison. That look, if p is smaller than alpha, well, hey, fantastic, fireworks go off, we're really happy, elated about it, because again, that means that my probability is less than my threshold for what I consider to be unlikely. And so that assumed null hypothesis was incorrect, and I get to reject it in favor of our claim or alternative hypothesis, whatever that claim may be, which again is happy days for us. We get to make that assertion. If only it was always the case though, because sometimes the p-value is greater than alpha. Bummer. Not happy about that at all, because what that means is I fail to reject. I don't get to make the claim that I wish to. To highlight it again, this does not mean that we're somehow asserting the null hypothesis. We're not saying, oh yeah, the status quo is true. All we're saying is that we cannot make the assertion that we wish to make. And that's all. Again, this is not making the claim that the alternative hypothesis is wrong. We're not admitting defeat altogether by saying our claim that we asserted was wrong. You know, we admit defeat. Instead, all we're saying is that there wasn't enough evidence. The evidence wasn't strong enough to support our claim. This is a really friendly way of, let's say we gather some evidence and it didn't support our claim, and we get up on a podium and we say, all right, guys, we did this test, and they're like, oh, what's the result? What's the result? And we'd say, well, really, there's no result. We cannot make a claim. We cannot make a claim. We'd like to be able to assert something, but unfortunately, if p is greater than alpha, we cannot. And so this is how we make our decision. So again, to build the argument up, you set up the hypotheses, you gather some sample information, you calculate a p-value, we'll get to it in a minute, and then it's the comparison, that p-value with alpha, that's going to dictate either amazing, we get to reject the status quo, or if p is greater than alpha, fail to reject. And so let's see a couple examples, kind of going through the arguments, and then maybe we can decide if a mistake was made or not. Here's our example. For the given scenario, determine the type of error that was made, if any. A study regarding the effects of television viewing on children reporting that children watch a mean of 4 hours of television per night. Kiko believes that the mean number of hours that children in her neighborhood watch television per night is not 4 hours. She performs a hypothesis test with 5% level of significance and computes a p-value of 3%. Should she reject or fail to reject the null hypothesis? And so this is our first little part here. Again, we're trying to figure out the status quo. What has always been? In this case, they're talking about a mean of 4 hours. Look, the mean is equal to 4. If you want to be fancy, you can write hours there. But the mean is equal to 4 hours. It is what it is. It is what it always has been. But Kiko here is looking at this going like, I don't think so. I know a lot of people, and they are not watching an average of 4. It may be greater, it may be less than, but it's not 4. And so the claim that's being made, the alternative hypothesis, is that the mean is not equal to 4 hours. If you remember, this level of significance, this 5, we often wrote as alpha. This p-value of 3%, we often wrote as p. And now it's time to make a decision here, reject or fail to reject. As a little note to self, reject is always p less than alpha. And then fail to reject is p greater than alpha. Well, we can actually look at our values up top. We have the numbers. Alpha, it says, is 5%, and my p-value is 3%. That comparison, hey, you betcha, is less than. Fantastic. Everyone's elated. Woohoo! Reject that null hypothesis. That Kiko gets to make that assertion. Her suspicions were correct. Unfortunately, maybe not, though. Let's see. Assume that in reality, like some time passes and they're able to gather this information. Children in her neighborhood, actually, they do watch a mean of 4 hours of television per night. Did she make a mistake or an error? Well, you can guess from my tone maybe that, yeah, indeed she did. The way I encourage you to think about this is there are really two types of mistakes that can be made, either type 1 or type 2. Again, type 1 is made if you reject. Type 2 is made if you fail to reject. You might be asking, reject or fail to reject what? It should be HO, the null hypothesis. Well, we rejected. Again, we were all elated, but we were wrong because they do watch 4 hours. That the null hypothesis should have been true. We should not have rejected. We made an error. That mistake is called a type 1 error. Type 1 is reject when you should not have. And that was indeed our mistake here. Bummer. Next example. For the given scenario, determine the type of error that was made, again, if any. Insurance companies commonly use 1,000 miles as the mean number of miles a car is driven per month. One insurance company claims that due to our more mobile society, the mean is more than 1,000 miles per month. The insurance company performs a hypothesis test and finds a p-value of 7% with a 10% level of significance. What should the company decide? So first we need to set up the claim. Again, the status quo. Is at the top a mean 1,000 hours? So that's what we'll start with here. The mean is equal to 1,000. This is miles, not hours. Here we go, miles. And our claim has something to do with the mean and 1,000, but we're interested that it's changed in some way. In this case, they think that it's more than 1,000 miles. And that's the claim that we're making. So we're right. I think it's greater than 1,000 hours. Now look, in order to make a decision, reject or fail to reject, it's always a comparison. P less than alpha, or unfortunately, P greater than alpha. Here, alpha refers to our level of significance. That's the 10% versus our P is 7%. And so we can write it over here that our P value equal to 7%. Ooh, fantastic, is indeed less than my 10%, my level of significance alpha, which fantastic for us. We get to reject the null hypothesis. Everything is turning up us, or in this case, insurance company. Well, let's see what actually happened. Assume that in reality, the mean number of miles a car is driven per month is 1,250 miles, and the average. Was an error made? Was there a mistake? They were claiming, or the status quo was 1,000. We thought it was greater than that. And actually, look at that. This is greater than 1,000 miles. In fact, quite a bit, 250 more. So yeah, quite a bit. So, our suspicions, our claim to reject the status quo was very correct. We made the correct decision indeed. And that's exactly what our test showed, and also apparently in reality showed as well. Let me wrap and recap with this. Hypothesis testings are really setting up an argument. You have to figure out what side or what claim we're trying to prove. Oftentimes there's a status quo, it's always been true, and then there's our claim that we want to show. And look, if everything shows up us, if our p-value is less than alpha, we get to reject and make our claim that we've always wanted to. Fantastic for us. And so the structure of these is very different from confidence intervals, but the overall inference is similar, that we take sample information, something that's anecdotal that moves around, and somehow we're able to, with a normal distribution, with probability, apply it to a population, be able to make these inferences, not just about the sample we gathered, but the population that it was gathered from. Look, if you liked the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.